what is the Enigma cipher and how does it work? Well, luckily I have with me a genuine World War II Enigma cipher machine. Here's a keyboard and here's a lamp board. To encrypt a letter I simply type it here. Let's encrypt the letter X. I type the letter X here and the letter S has lit up. But if I type X again, now the letter G has lit up. So the same letter is being encrypted in different ways. Now how's that happening? Let's have a look inside. Between the keyboard and the lamp board, the electrical signal passes through these three rotors. Now, what's really, really important about Enigma is that every time I type a letter, this rotor moves. In fact, when this rotor's completed one revolution, it kicks this one. And when this one completes a revolution, it kicks this one. So these rotors are always going to be in different positions. These rotors determine the form of encryption, therefore the form of encryption is going to be constantly changing. There's much more to Enigma than just these three rotors, as you'll see in the rest of this section. But essentially, it's these constantly moving rotors and their constantly moving mode of encryption that makes Enigma such a difficult code to break. So let's just summarize the Enigma machine by encoding and decoding a message. Let's encode the message OK. O gives me a P, K gives me an H. I would now send PH to somebody else. If that person wanted to decode the message, they would have to have an Enigma machine set up in exactly the same way as I had it when I sent the message. This rotor's moved forward 2 places since I started sending the message, so let's move it back 2 places. Now, if PH is typed in, it should give me the original message. P gives me O and H gives me K. So I can decode the message as long as I've got an Enigma machine and it's set up in exactly the same way as the sender. So here's a rotor from an Enigma cipher machine. On one side you've got 26 contacts. On the other side you've got 26 contacts. Now, in between these contacts, the wiring is like spaghetti. So the contacts aren't directly related to each other. What this means is that if I type the letter A, this sends an electrical signal into, say, the top contact. It emerges, perhaps, at the bottom contact. So the letter is being encrypted by the confused wiring inside the rotor. Now, if I type the letter A again, well, the first thing that happens is that the rotor moves by 1 position. The signal still enters at the top, but now that's a different contact. So the current emerges at a different position, perhaps to one side. And it's this constantly moving rotor and the complex wiring inside it that determines the encryption of a letter. So here's an Enigma cable with a plug at one end and a plug at the other end. Now these plugs were inserted in the Enigma machine below the keyboard in the plug board. Here you can see some plugs in place. There were 10 cables, which means there were 20 plugs. Those 20 plugs sat among 26 holes, 1 hole for every letter of the alphabet. Now the thing is, there are a huge number of ways that you can arrange 20 plugs among 26 holes. It turns out that there are roughly 100 million combinations.